Let's start this analysis from the perspective of a sinusoidal current source IA. This means we need to remove the voltage source EB by replacing with a short or a low impedance path. Note when we redraw the as-analyzed circuit, including the short, the nature of this circuit has fundamentally changed. Note that any current traveling out of an impedance element Z3 will travel through the zero impedance short rather than the path afforded by impedance element Z4. The inclusion of the short has effectively removed impedance element Z4 from consideration. No current will travel through impedance element Z4, and there will be no voltage drop across it. I4 equals 0 and V4 equals 0. With impedance element Z4 removed from consideration, current will flow through the circuit as indicated. Sinusoidal AC current source IA will force 25 mA at an angle of 0 degrees through impedance element Z1. I1 equals 25 mA at an angle of 0 degrees, traveling left to right. Current will split into two paths, one through impedance element Z2 and the other through impedance element Z3. An application of the current divider rule demonstrates I2 will be 15 mA at an angle of 53.1 degrees, traveling top to bottom. A subsequent application of Kirchoff's current law demonstrates I3 will be the remaining 20 mA at an angle of 36.9 degrees, traveling top to bottom. Let's now consider voltage. An application of Ohm's law demonstrates V1 will be 6 volts at an angle of 0 degrees, oriented positive to negative, left to right. Another application of Ohm's law demonstrates V2 will be 6 volts at an angle of negative 36.9 degrees, oriented positive to negative, top to bottom. Given impedance element Z2 and Z3 are in parallel with one another, V3 will also be 6 volts at an angle of negative 36.9 degrees, oriented positive to negative, top to bottom. The series parallel analysis from the perspective of current source IA is now complete. Let's put these values to the side and now do the same thing for voltage source EB. When sinusoidal AC voltage source EB is our source of interest, we need to remove sinusoidal AC current source IA by replacing it with open. Note, when the circuit is redrawn, the as-analyzed circuit, including the open, the nature of this circuit is fundamentally changed in that no current will travel through impedance element Z1. The inclusion of this open has effectively removed impedance element Z1 from consideration. With no current traveling through it, there will be no voltage drop across it. V1 equals 0 and I1 equals 0. It may help to again redraw this circuit when impedance element Z1 has been removed from consideration. A Kirchoff's current law analysis of this modified circuit indicates two current paths, one through the series combination of impedance element Z2 and Z3, and another through impedance element Z4. An application of the AC voltage divider rule demonstrates V3 will be 10.8 volts at an angle of 53.1 degrees, pointed positive to negative, bottom to top. A subsequent application of Kirchoff's voltage law demonstrates V2 will be the remaining 14.4 volts at an angle of negative 36.9 degrees, positive to negative, top to bottom. For our as-drawn circuit, voltage across impedance element Z4 will be equal to EB. V4 therefore equals 18 volts at an angle of 0 degrees, oriented positive to negative, top to bottom. Let's now consider current. An application of Ohm's law demonstrates I2 will be 36 mA at an angle of 53.1 degrees, traveling bottom to top. Given impedance elements Z2 and Z3 are in series with one another, I3 will also be 36 mA at an angle of 53.1 degrees, only this time the assumed direction of travel is top to bottom. Finally, another application of Ohm's law demonstrates I4 will be 30 mA at an angle of negative 85 degrees, traveling top to bottom. The series parallel circuit analysis from the perspective of only voltage source EB is now complete. Now that we've completed independent analysis of this circuit from the perspective of all sources, the only task remaining us is to summate these effects accounted for magnitude, phase shift, polarity, and direction. Again, before doing so, note how the inclusion of shorts and opens have fundamentally changed the nature of this circuit. Shorting out EB effectively removes impedance element Z4 from consideration. In contrast, the inclusion of the open effectively removes impedance element Z1 from consideration. From the perspective of one source or another, this same circuit exhibits fundamentally different properties. Let's summate individual properties. Given current source IA induces 25 milliamperes at an angle of 0 degrees through impedance element Z1 left to right, and voltage source EB induces no current through impedance element Z1, it can be said when these effects are superimposed upon one another, impedance element Z1 ultimately experiences 25 milliamperes of current at an angle of 0 degrees traveling left to right. Following similar methodology, the voltage drop across impedance element Z1 is 6 volts at an angle of 0 degrees. With respect to impedance element Z2, it appears current source IA and voltage source EB are aiding one another, and that current direction and polarity are the same. In this scenario, we'll assume top to bottom is positive and simply add the effects. Impedance element Z2 ultimately experiences 51 milliamperes of current at an angle of 53.1 degrees traveling top to bottom. Following similar methodology, the voltage drop across impedance element Z2 is 20.4 volts at an angle of negative 36.9 degrees, positive to negative, top to bottom. With respect to impedance element Z3, it appears current source IA and voltage source EB are opposing one another, and that current direction and polarity are opposite. It appears voltage source EB's magnitude contribution is larger, so we'll just assume the bottom is positive and the top is negative, and simply subtract current source IA's contribution. It can be said that when these effects are superimposed upon one another, impedance element Z3 ultimately experiences 41.2 milliamperes at an angle of 82.2 degrees, traveling bottom to top. Finally, given current source IA induces no current through impedance element Z4, and voltage source EB induces 30 milliamperes at an angle of negative 85 degrees through impedance element Z4 top to bottom, it can be said when these effects are superimposed upon one another, impedance element Z4 ultimately experiences 30 milliamperes of current at an angle of negative 85 degrees, traveling top to bottom. Following similar methodology, the voltage drop across impedance element Z4 is 18 volts at an angle of 0 degrees, oriented positive to negative, top to bottom. Now that the final summated voltage and current figures have been calculated using the superposition theorem, one is free to perform analysis of other nonlinear properties like power using these final figures. Alright, let's bring this introductory lecture to a close. For those seeking additional guidance on this topic, rest easy. I'll soon publish another lecture featuring solely illustrated examples of superposition theorems applied to AC circuits. Until then, let me remind you the superposition theorem isn't necessarily a new technique, but rather repetitive series parallel circuit analysis, a technique you've got ample experience with by now. Very often, it isn't necessarily the electrical concepts, but rather organizing the results of the independent analyses and accounting for magnitude, phase shift, polarity, and direction that trips students up when employing superposition theorem for the first time. Current with a wrong direction or voltage with a wrong polarity or failing to take into account phase shift can have disastrous consequences. Take your time and stay organized when summating results. Pick a direction and just stick with it. In conclusion, we learned to employ the superposition theorem in an effort to solve for desired electrical quantities for AC circuits with more than one source. We learned that linear properties like voltage and current can be summated, accounting for magnitude, phase shift, polarity, and direction. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.